Initially, we have started about the yielding criteria. You remember, I think. Okay, so based on the yielding criteria, we have why we are going for the yielding criteria because this is essential or this is need to find out some empirical relationship. Okay, so there are two categories. One we have done about the Tresca criteria or the maximum shear stress, and the second one we have the von Mises or this is a distortion energy. So before that, when we went for these two criteria, von Mises and Vitreska, so before that we have gone through the maximum shear stress. Okay, of course we have covered in the beginning also. Based on the maximum shear stress, we have understood that using the help of the Mohr circle, so we have to define or we have to find out a relationship between the normal stress and the shear stress. Okay, so if you remember, we talked about the tau 1 equal to sigma 1 minus sigma 2 by 2. Similarly, tau 2 and tau 3 also we have derived, right? Then also we have talked about the deviatoric or the reduced component stress. So when we talked about the hydrostatic stress, maybe a long time before we talked, we summarize that this is the average of the principal stresses. For example, if sigma h equal to sigma 1 plus sigma 2 plus sigma 3 divided by 3. Okay, this is known as the hydrostatic stress. Then we talked about what is the deviatoric stress. So basically, this is this component actually when you want to find out, and this is the subtracting of the hydrostatic stress, so that if you want to find out sigma 1 dash, okay, because your hydrostatic stress is sigma h, right? So if you want to find out sigma 1 dash equal to sigma 1 minus sigma h, okay, so you will just subtract from the subtract, okay, sigma 1 dash equal to sigma 1 minus sigma h, right? These are we covered. Then we talked about the Tresca criteria. Okay, so Tresca criteria also, if you remember that equation, we mentioned that sigma max minus sigma min divided by 2 equal to sigma f by 2. Okay, the flow stress by 2. But if you want to cancel both these at 2, so you will find with sigma max minus sigma min equal. Is it clear? Or we have discussed these things?
Yes, sir.
Yes, sir. Then next we talked about the von Mises criteria also. So if you remember that equation, we have derived root over 1 by 2 into sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay, so these are also we have discussed. And finally also we have done two numericals. But when you have the shear stress actually, so I didn't derive all the the equation because these are already we have derived in composite materials. So I didn't derive only the one basic equation we have derived. But if you have, based on the numerical two, actually what we have done. So that is the equation, whatever we have derived, root over 1 by 2 into sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square. These are what we derived. But here, if you have the shear stress, okay, if you have the shear stress, I think you can go back the shear stress. Okay, so this slide, I think we have covered. Okay, so if you want to go to the shear stress, you have 1 by root 2. Okay, this is just only I converted 1 by root 2. Sigma x minus sigma y square plus sigma y minus sigma z square plus sigma z minus sigma x square plus 6 into tau xy square plus tau yz square plus tau xz square. Okay, so this is the equation. I'm not going to derive that one. So based on this, we have done these two numericals. Okay, just you can cross check. Maybe I will upload, I think, whatever the remaining portion, maybe 3-4 slides I have. So I will update this one by today. Okay. So this today we will talk about the yield locus also. So this one also, if you remember, maybe some slides back also I have covered this yield locus, maybe in some other way. So for a biaxial plane stress condition, so if you want to take this, the ellipse. So here, normally when we are talking about the biaxial plane stress condition, so you have to assume something because when we are talking, if any mechanical deformation you are making, because this deformation actually you are making in all the three directions. You are not thinking, you are not doing that only one direction you are making. Whenever it is making the plastic deformation, you are making it in all the three directions. But sometimes we cannot calculate in a proper way, so that's why we are going for the empirical relation. So in that case, you have to think that maybe somewhere we have to assume. So similarly, for biaxial plane stress condition, if you are assuming this sigma 2 equal to 0, whatever we have derived in the Bernoulli's criteria, so mathematically you can derive like sigma 1 square plus sigma 3 square minus sigma 1 into sigma 3 equal to sigma 0 square. Okay, so why you have no sigma 2? Because we have assumed that sigma 2 equal to 0. Okay, so if you will put in the Bernoulli's criteria and instead of the sigma 2, if you will put in 0, so you will find this equation. right? And if we'll consider this yield criteria of the plane stress, okay, so normally if you want to find out the major axis, okay, for example, your major axis is here, this one, because this is a bigger side, and the minor axis is here. Okay, so if we'll calculate, because this is a triangle now, okay, and this side is 90 degree. So if you want to calculate from that triangle, so you will find this line or this dimension is root 2 sigma 0, and this is known as the major semi-axis. And whereas if you will calculate the minor semi-axis, this is root over 2 by 3 into sigma 0. Okay, so this distance from here to here, because this is no smaller side, so this is known as the minor semi-axis, and this is the higher side, so this is known as the major semi-axis. And the plot, whenever we are measuring or whenever we are drawing and vetting based on this equation, sigma 1 square plus sigma 3 square minus sigma 1 sigma 3 equal to sigma 0 square, this is known as the yield locus. Okay, so that equation actually you are putting in a graphical representation. Okay, or maybe you are putting that ellipse representation. And from yield locus, actually, you will find several observations. And what are the basic observation you have? The yield locus for the maximum sources critical criteria falls inside the von Mises yield ellipse. Okay, so you will find only inside, you cannot go beyond that. And note that the two yielding criteria predict the same yield stress for conditions of uniaxial stress and balanced biaxial stress. If you want to assume sigma equal to sigma 3, then you will find also one more condition. So these are the basic, like, some of the observation what you are getting from the von Mises criteria, or whatever we are getting from the Tresca criteria. Okay. What we have observed also in the beginning, if you want to, what I was just giving the recap. So if you have the octahedral shear stress and the shear strength, how actually you will find. So initially, if you remember, I was telling that equation, the hydrostatic press sigma h equal to sigma 1 plus sigma 2 plus sigma 3 by 3. So here also, if you have a set of stress function without, this is a many shear stress if you have, or many shear strength you have. So what kind of equation you will get again? The sigma octahedral equal to sigma 1 plus sigma 2 plus sigma 3 by 3. Okay, because if you have 3 or if you have more than 1, so you are making the average of the principal stresses, right? So similarly, if you have the octahedral shear stress tau octahedral, so you will find this equation tau oct equal to 1 by 3 into sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square, and this is root over. So I made it 1 by 2. Okay, but in that case, what we are getting? We are getting 1 by root 2 there. Okay, so we do not need to go big derivation there. Just only you have to remember, if more than two stresses are there, or more than two principal stresses are there, so what are the equations you are getting, right? Is it clear? Yeah.
Yes, sir.
And similarly, if you have the, from that two equation, actually, if you want to derive again, if you go step by step, then again you will find this equation. Okay, these two equations. And whereas if you have the strain is available there, the strain is existing there, then the epsilon octahedral equal to the epsilon 1 plus epsilon 2 plus epsilon 3 divided by 3. Similarly, if you have the shear strain is available, or the shear strain is existing, so here you can see this is 1 by 3 and this equation is there, but here it is coming 2 by 3 and this equation is there. Okay, so these are the basic, of course, whatever we have done in the beginning. Okay, the two stresses or the three stresses we have done. But if you have more than the stresses also, you can calculate. There is no obstacle that only if you have two stresses or three stresses you can do. More than two or three stresses also you can calculate. Okay, but somewhere you cannot find the very exact the equation. So that's why we are assuming something like our thermodynamics. We are assuming something. So based on this assumption, we are going towards the empirical relation. Based on this, we are calculating something. Okay. Okay. So similarly, another one also, invariant stress and strain. So what is actually invariant stress and strain? So it is frequently useful to simplify the representation of a complex state of stress or strain by means of invariant functions of stress and strain. Okay, so for example, if you have a complex set, so you cannot tell, maybe in the exam also sometimes you are doing, so when you cannot calculate in a proper way, then it is very difficult. You are just putting what you thought. But here what you have to observe, you have to tell that, let's say, for example, this is considered as X, then only you have to find out something. Okay, so here also, if you have the most frequently used invariant function to describe the plastic deformation is effective stress and the effective strain. So sometimes, if we are teaching, or maybe if you are studying, so we are telling that we are studying maybe 10 hours, or maybe we are studying for 5 hours. But how much is the effective study hour? Okay, so this is basically known as the, here also we have to calculate this how much of the effective stress. So I mentioned this one, the normal stress we are taking sigma, so you can make it a sigma bar, and the effective strain is epsilon bar. So you can find out again this equation, sigma bar equal to root over 2 by 2 into sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma square the root over. Okay, so similarly if you want to go to the epsilon, so you can find out the d epsilon bar equal to root 2 divided by 3 of this equation. Okay, just you can, this is all the equations are almost same. Only the first variant is only different. You know, the constant, let's say 0, root over 2 by 3, or maybe root over 2 by 2, or maybe 1 by 2, or maybe 1 by root 2, then 2 by 3. You know, in the previous slides we have discussed. Okay, these are just have a recap and make it in one page. Let's say if you want to remember all the equations in one page, just you can write. For example, this is the normal hydrostatic stress, or maybe this is deviated stress, and this is the one Mises equation or the Tresca equation, and this is octahedral equation, then this is the invariant stress and strain equation. Then we will find out it's very clear, and this is very easy, not so hard. Okay. In the last slide, or the last talk of this presentation, is we have the slip line field theory. And if you remember, we have talked about the the polycrystalline material. When we talked about the slip in polycrystalline material, I have given one example of the slip line, one schematic photo with the slip line. Okay, so here also in many practical problems such as rolling and street drawing, all displacements can be considered to be limited to the xy plane, so that the strengths in the z direction can be neglected in the analysis. So sometimes, you know what I told maybe sometimes ago, that if you have the plastic deformation, that means all this deformation is happening in all the three directions, x, y, and z. But to make it simpler, or to make it easier, so we have to at least avoid one, or we have to assume that, for example, one part will be zero, right? For example, if you are making an xy plane, so the z direction, or maybe x direction, y direction we are calculating, or we are considering, z direction we are not considering, and we are neglected as we are considering as zero, or we are neglecting. Okay, and this is known as the condition of plane strain. Condition of plane strain. So that means only we are considering about the xy plane, or maybe yz plane. Only two xy plane we are considering, right? When a problem is too difficult to one exact three-dimensional solution, a good indication of the stresses often can be obtained by consideration of the analogous plane strain problem. Sometimes when we are facing some problem, then we have to try to resolve it. So every time I'm focusing on, when we are engineers, so we have to find out the problem. At the same time, also we have to give the solution. You cannot tell that no, I cannot do this one, so just leave it, or just forget about this one. We have to give the solution. So similarly, if you will see here, two schematic diagram I have given you. So the methods of developing the plastic constraint where we are getting. So if you think about our, for example, the forging, let's say, of course, we will talk about forging a little bit today. So if you will see here, you have the die here. Okay, you are applying the force here, and you have the material here. So that means you have to press here. Okay, what is the size of the, or according to the size of the die, then only you will get that kind of product. Okay, but this, when you are pressing this one, so this plastic deformation happening in all the three directions, x direction, y direction, and z direction. But at least one direction you have to neglect. Similarly, if another schematic diagram also, if you want to see here, we have the the rigid surface here, but there is a small space that it can go inside. Probably I will show also today at the forging, the types of the classification of forging, maybe one or two slides, so that at least you can understand how you are not thinking about only we are pressing from the top. But this depends upon the die also. Maybe last time I think Charles was asking about the, one question about whether we are repeatedly we are doing work, right? So this depends upon the die, whether this die is everywhere, this is fixed here, or maybe there is some gap here, or maybe in other option you have. But at least we have to make it one parameter should be zero. Since a plastic material tends to deform in all directions to develop a plane strain condition, it is necessary to constant flow in one direction. Okay, is it clear now? Yeah.
Yes, sir.
Okay. So the last slide, this one, probably I just put again in some, summarize this one. So for a state of plane strain, the maximum shear stress and the bound necessity factor are equivalent. So if you want to now, like, that's why I told you in one page actually, maybe you can put it like, all the columns. This is X, Y, Z. For example, whatever the conditions actually we have studied, you can make it. And the moment you will make it, you will find that the maximum shear stress and the von Mises criteria are almost equivalent. And it can be considered that the two-dimensional plastic flow will begin when the shear stress reaches a critical value of K. Okay, so K is the yield stress in pure stress. Slip line field theory is based on the fact that any general state of stress in plane strain consists of pure stress and the hydrostatic pressure. So these are also we have talked. Okay, so it consists of actually you have the hydrostatic pressure and also you have the shear stress. And also one more thing for such a non-strain hardening material, K, state of pure stress, what we have discussed now, and is everywhere constant, but P, the hydrostatic state of stress may vary. Because sometimes, like, I remember sometimes I give you, the copper sulfate example. So whenever you are decomposing something, so at least one parameter you have to fix it, and other parameter you have to vary. But the moment you will vary both the parameter, then it will be much more difficult because you cannot judge it or you cannot analyze it. So similarly here, if you have the state of pure stress, and if this state of pure stress is everywhere constant, or you are making this constant, but at the same time also you have to vary the hydrostatic stress, for example, the P, then only you have to adjust something. And at the same time also, one more important factor is here, the lines of the maximum shear stress occur. Because if you will see the lines of the shear stress, in which line it is passing. So the lines of maximum shear stress occur in two orthogonal direction. One is angle alpha, and second one is angle beta. Okay, so in which way actually it is moving, or in which way we are finding, the ellipse, if you want to remember, one is the major axis we are talking and one is the minor axis we are talking. So in which angle, so if you want to remember that critical resolve shear stress we have discussed about, one is theta and one is phi. Okay, and these lines of maximum shear stress are known as the slip lines. Okay, so this is all about the plastic deformation, but we have covered in model. Okay, any question up to now?
No, sir.
Is it clear? And we have derived small equations, and based on this also we have done a few numericals. Okay, so then we have to go for the module 3 actually. So module 3 is a forging process. So can somebody tell what is forging process? Anyone?
Pressing metal parts to make almost equal to the required part,
Almost
equal to the required shape.
required shape.
Yes, sir.
Any other? Any other?
Sir, it is mainly a shaping operation.
Shaping operation. Okay. Any other?
Using force to change the shape of an object to obtain the required product.
So they use compressive forces, sir.
Use compressive process. Yeah. Any other? Okay. 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 I think almost like when variety of answer is coming, then you have to accumulate everything. Okay. So it will be all these students who have told the right way. So just only today we'll go a little bit of introduction. So forging process actually we will introduce this one. Then also we'll go the classification of forging process. Okay. Only 2-3 slides I will cover today. Okay. Yeah. So the forging actually, okay, I mentioned here the forging is the working of metal into a useful shape by hammering or pressing. Okay, so you cannot tell that only pressing, because if you remember, every time I'm giving the example of the blacksmith. Okay, so if you go to see the blacksmith, they are not pressing there. Okay, so pressing means you have to go for any you should have some equipment, or you should have some technique there, right? Hammering means you have to do manual. You have to, of course, you have to press it, but you have to force it with, by using your hand. Okay. And it is the oldest of the metalworking arts, having its origin with the primitive blacksmiths or the biblical times. Okay, so maybe ancient time, maybe you can go to that book actually. So in the book actually, if you want to study the like a little story or maybe history from where it started, and it is clearly mentioned. So I didn't put actually everything because in PPT we cannot put everything. But still, if you want or if you are interested, and this is the most oldest one, if you want to go for or compare with the rolling or maybe extruder, the forging is the oldest one. Okay, so we are comparing with the blacksmith. And the development of machinery to replace the arm of the smith occurred early during the Industrial Revolution. And from here on, from forging onwards, it started or it went to for the Industrial Revolution. And today there is a wide variety of forging machinery which is capable of making parts ranging in size from a bolt to a turbine rotor or an entire airplane wing. So of course we will go maybe there is a small chapter we have forging equipment. Okay, so maybe I do not think we will cover everything, but if somebody wants to study in detail actually, so also you can remember here. So the capable of making parts ranging in size from bolt, this is a very small part to a turbine rotor, little medium part. Then you have to go for entire airplane wing. Okay, so that means from the smaller part to the bigger part or the larger part also, we are going or we are preparing with the help of the forging process. And two major classes of equipments are used for forging operation. So one is the forging hammer or the drop hammer. Okay, so that is known as the manual forging process or what the hammering we are talking about. Okay, and this delivers rapid impact blow to the surface of the metal. And this rapid impact because you are giving the force very with a high speed or with a high velocity while the forging press subjects the metal to a slow speed compressive force. Okay, maybe somebody was talking about the compressive force, but of course, when you are writing the definition, you have to also, in case of mine also, I just wrote forging the working of metal. Okay, and also you have to write what kind of forces you are giving them. That is important. So here it is written that the forging press subjects the metal to a slow speed, whereas if you compare with the hammering, this is a high speed. But here this is you are applying the compressive force, right? Is it clear? Yeah. Okay.
Yes, sir.
Am I audible?
Yes, yes, sir.
Sir, you're audible, sir.
Yeah. So the next one we have the classification. When we are going to the classification, one classification I have told you that previous one is hammering and one is pressing. This is one kind of classification. And second one also, if you remember, we have talked about the the hot working, cold working, and warm working. So based on that temperature, with the help of the temperature or with respect to the temperature, the forging also may be carried out at room temperature or known as cold forging, or at elevated temperature known as warm or hot forging, depending upon the homologous temperature. If you are considering with respect to the temperature, then also you can define or you can classify as cold forging or maybe hot or warm forging. And how to define that cold forging? The cold forging requires higher forces. Cold forging requires higher forces because of the high strength of the workpiece material, and the workpiece material must possess sufficient tilt at room temperature to undergo the necessary deformation without cracking. Because that part is much more important without cracking. Because if you are going to again to find out some crack, then maybe this is a waste. Okay, or maybe this is not required. So that means in cold forging, you are giving higher forces. Okay, and the cold forge parts have a good surface finish and dimensional accuracy. Also, maybe you will find another part also after the forging, whether this is cold forging or maybe this is hot forging, whether this is needed at the the finishing operation is required or not. That is also one more question again will come. And the hot forging requires the lower forces. You can just define here. The cold forging requires the higher forces, whereas the hot forging requires the lower forces. But the dimensional accuracy and the surface finish of the parts are not as good as in cold forging. Okay, so there are two things. One is the cold forging, you are using the high forces, whereas the hot forging, you are using the low forces. And in cold forging, the whatever the parts you are getting or whatever the product you are getting have a good surface finish, whereas in hot forging, you are not getting the good surface finish. And the forging is generally a subject to additional finishing operation. Okay, you have to go for the additional finishing operation. If you remember, in machining when we are talking about, in some machining process also you have to go for the finishing operation. Such as what kind of finishing operation you need, such as heat treatment or the heat treating to modify the properties and machining to obtain accurate final dimension and good surface. So that means, when we are talking about the residual stresses, or maybe if inside you have some any cracks or maybe any blowholes inside, I'm not talking outside, inside if you have, then you have to go for the heat treatment or maybe you have to go for the hot forcing again. And similarly, if you want to go for the good surface finish, because if somewhere like if you are making hot forcing, so that means your surface finish is not good, then you have to go for some another surface, another process. And one more thing is also you have whatever the shapes you require or the customer requires this kind of dimension, then you have to also go for a different process. For example, it may be in the beginning of the class, somebody was asking, the shear stress when we are cutting. Okay, because this is a big billet is coming or the big plate is coming, and that plate you cannot keep. Whether you have to roll it if this is very thin, but the moment you have this thick material or the thick sheet, then you have to. It's very difficult to roll it. So you have to cut it to maybe small pieces, and these finishing operations can be minimized by precision forging, which is an important example of net set or near set forming process. Even if you remember also when we talked about the plastic deformation metal in the beginning, what is the introduction of the basic mechanical working. There also we have talked about net shape, or maybe that is very close to that particular shape what we are exactly wanting. Right? Is it clear? Yes. So I think this is the last slide I have prepared for you. So another classification, now three classification here we have. One is you have the the hammering or the pressing, and second one we have the based on the temperature, the cold working or maybe the hot working or warm working. Then another difference among the forging operation is the degree to which the flow of the work metal is constrained by the dies. Okay, which the flow of the work metal is constrained by the dies. So how the dies actually you are keeping and what kind of dies you are keeping. So based on this or with respect to that also you can classify. And by this classification there are three types of forging operations are there. Okay, so one is known as the open die forging, and the second one is known as the impression die forging, and third one is known as the flashless forging. Okay, so I have given three schematic diagram here, and also one line just I have mentioned here. In case of open die forging, the work is compressed between two flat or almost flat dies, thus allowing the metal to flow without the constraint in a lateral direction related to the die surface. So if you fill the schematic diagram one, the first one. Okay, so there are two flat surface or the two die you can see on the bottom one die and the top one die. So inside you have the workpiece. Okay, and this is the upper die and this is the lower die. And whereas the lower die is stationary, so this is not moving, only the upper die is, and you are giving the force on the top die. Okay, and also with a velocity this is coming, so you have to press it. So this is known as the open die force. So that means this is totally open. Okay, so this is known as the open die force. And whereas if you want to go for the impression die force, the second part, the schematic diagram, the die surfaces contain a shape or impression that is imparted to the work during compression. The die is not flat, you can see here. Okay, so there is some little a different structure is there. So based on this die, also you can find out the product. Okay, like mold, what we are calling in casting or the manufacturing process, what you have studied. Okay, so based on this mold or based on the design of the mold, you can prepare that one. But here one more interesting thing you will get, a portion of the work metal flows beyond the die impression to form flash. Okay, you can see here, this is the upper die on the upper part, and this is the lower die, and the lower die is stationary, and the workpiece is inside here, and the moment you are giving the force with the velocity from the top, and you will find some of the material. Okay, some of the material, whatever the inside, the material you have put inside, and some of the material it will come out. And this material is known as the flash, or this is known as the excessive metals or the excessive materials. And the flash is excess metal that must be trimmed off later. And the moment you will finish it, and whatever because this like waste material, or this like for example, if you remember, when we are putting gum in the envelope, let's say if you are putting some letters and putting the gum, and if the gum is a little more, then it will come out from that paper. Okay, then you have to remove it, or you have to erase it, or you have to take it out. So similarly, if you want to the flash is coming, and this is waste material, or not waste, excess material, you can say that material also you can use in other other processes. So this is known as the impression die force. And the third one we have the flashless force. Flashless. So what is happening in the flashless force? The work is completely constrained within the die, and no excess flash is produced. You can see here. Okay, so this is the workpiece here in between, and this is the die, and the die is stationary, and you have the punch here. Okay, so that means you are pushing within the die, because this die is, you can see here, and here there is a gap. and the punch is coming within the die here. And whenever you are pressing with the, whenever you are giving the force with a certain velocity, and this is coming, but whatever the material you are putting here, but you have to find out there exactly. Okay, so that means whatever the volume of the initial raw material, and also you will find exactly whatever the volume of after the forcing process. So the work is completely constant within the die, and no excess flux is produced because there is no gap here. So you cannot find the flux material. And the volume of the starting workpiece, you can imagine here, the volume of the starting workpiece must be controlled very closely so that it matches the volume of the die cavity. Okay, so whatever the volume of the material you have put in the beginning and the volume of the die cavity, whatever you have, and this should be, the close, or this should be equal. So this is known as the fluxless force. Yeah. Question open now.
Yes, sir.
Yes, sir, or no, sir? Okay, so if you have any question, just you can ask me. And in the you have the cat one, I think 12, right?